Good morning, everybody. And in the previous class, we have discussed about the heavy powders and the light powders. So, in the previous class, I am saying that in the heavy powders, the small particles may combine or may bind with the large particles. So that's why it's have low bulk volume and the higher bulk density. So during compressibility process in case of tablet manufacturing process, every time the heavy powders are recommended for the compressions because the elastic deformations in case of heavy powders are less because it have no porosity and lesser porosity than the light powders. So when we come into the light powders, where the particles are loosely packed, so lots of gaps is there in between the particles. So that's why the lots of gaps presence that causes the light powders have high bulk volume and the low bulk density. So when the high bulk volume is come, the elastic deformation natures also present in the light powders. So what is elastic deformations? So when any powders you are trying to compress, but it is not compressible at that moment, this is called the elastic deformations because they have to try to return their backstage or back natures. So that time the powder is not compressible conditions. So what are the importance of these powders? When in compressions process, all time recommended the heavy powders rather than the light powders because you can easily compress the heavy powders because their large number of particles are bound with the smaller number of particles. So that's why the space in between the particles is lesser than the light powders. So here an example is there that capsule cell filling. Capsules have two parts. One is capsule body and one is capsule cap. So when you fill the capsule cell on a proper filling machine and you fill the light powder granules, so that's time what is happened that you fill the powders in a proper quantity on the sample cell, but you can not adjust the capsule cap with the body because the loud powders are not compressible. So that time they can not adjust it with the body and the caps. So when heavy powder is filled by this process, the heavy powder is easily settled down on the bottom of the capsules and it have plastic deformation because it have the smaller particles bind with the larger particles and the laser porous in natures. So that time you can easily attach the cap with the body. So it is the advantages of the heavy powders and disadvantages with the light powders. So now we come in the determinations of bulk density, tap density and true density by one important apparatus. It is called the bulk density apparatus. Depending on the pharmacopoeia, each and every process, depending on the pharmacopoeia, they can prepare this bulk density apparatus depending on the specification of pharmacopoeia. So what are the specification is present in this process? The bulk density apparatus is now automatic bulk density apparatus is now available in our market with a true graduated glass cylinder present or attached with this bulk density apparatus. In this process, we can easily calculate it, the bulk density, tap density and true density of any powders like pharmaceutical powders or non-pharmaceutical powders. So in this process, these two graduated cylinders attached with the cushions bed which can protect the glass cylinder from the breakables, from the breakage during tap density measurements. So you can fill the powder or sand with a certain amount in the graduated cylinder, adjusted the knob and spring and start the apparatus. So first, in the previous class I am saying that what is bulk volume. If you take the 50 gram of powders and fill into or put into the graduated cylinders, so that time it is your mass of the volume equals to 50 gram, and this 50 gram mass of the volume indicated a certain amount of level on the measuring cylinders, so that is the bulk volume. So when you the mass of the volume divided by the bulk of the volume, you can get the bulk density of the process. So in this process is same. You can take the 50 gram of pharmaceutical powders or any sand and put into the measuring cylinders and get started the apparatus. Okay, so first process you can get the bulk density of the process, and after 2 times tapping you can get the true density of the process. So after getting the true density, you can get the 100 tappings by the process or 50 tappings. The 100 tappings and 50 tappings by this process, you can get the tap density of the process. So after each and every tap, you can get the tap volume. So the total mass of the powder is fixed, it is constant, and divided by the tap volume, you can get the tap density of the process. So it is the exact mathematical method of bulk density determinations and tap density determinations. But in this process, we can get the true density, not the exact values. Though if you get the true density with the exact value, we can use 2 important methods which we depend on different types of powders. This powder is porous powder or non-porous powder. If you had the porous powder, you can get the true density by the process, means weight of the powder divided by true volume of the powder, that is the true density. If you have the porous types of powders, you can determine the true density by gas displacement method, and if you have the non-porous powder, you can determine the true density or true volume by the liquid displacement methods. So first here we come in the gas displacement methods. You can show in the diagram that the gas displacement methods divide in 3 or 4 different types of process. First one is sample cells, next one is vacuum. A cylindrical valve is attached with these apparatus, and the bottom of the apparatus one variable volume piston is there, which can directly attached with a electrical resistance measurement apparatus. In this process, the main motive is to determine the porosity, what is the true porous density or true volume, by using 2 types of ideal gas. One is helium and one is the nitrogens. Now in this process, most popular usable gas is the helium gas, because it have the lower particle size than the nitrogens, and it is easily bind with the particles, but it is not absorbed by the materials. Helium penetrates in smallest pores and crevices easily, so that's why the helium is chosen for these methods. So in this process, first we have to calibrate these apparatus by using some constant spheres. So in this process, when we get the true density or true volume of any porous material, we can imagine that this porous material are spherical in shape. So according to sphere or spherical, we can also calibrate the pygnometer or the sample holders. So how to calibrate? So we can using here some stainless steel spheres, which by this process we can get a constant value of true volume and true density of a spheres. So first we can calculate it the empty pygnometer determination, volume of empty pygnometer determination. So how to calculate it? In this process, the sample cell is removed here in the presence air, which can remove by using vacuum pump. And then we can apply or introduce the helium gas through the sample cell, and a pressure created by the pressure valve or pressure gauge, a unique pressure reading which is shown on the pressure gauge. Okay, so in this pressure we can calculate it the reading, that is U1, because it is empty cell, no sample is there, so that's why we can get a reading, that is U1. U1 is a constant, is all time when you get the porous or calibrate these pygnometer or instruments. So you can using the empty pygnometer determination volume, that is E1. Next we come in the calibrations of pygnometer. So how to calculate it, how to calibrate that? The stainless steel sphere put on the sample cell, and the process is same, that the excess amount of air is present in this cell, you can remove by using vacuum pump. After removing, you can seal the sample cell and introduced the helium gas into sample cells and applying the piston for adjusting the pressures. So when your pressure adjusted, automatically the helium gas entrapped the porous spaces is there in between the stainless steels, and these entrapment pressures is directly denoted or show on the pressure gauge, that is U2, that is a reading. So how to determine the volume of sample? Easily you can you can minus the U2 value from the U1 value, so you can get the exact amount of helium is entrapped in between the process. So by this process, by these equations, we can calculate the true volume of the samples. The Vt equals to, it is a true volume, in the bracket Vc. Vc means the true volume of stainless steel spheres, that you can take the 20 gram, 50 gram, 30 gram, that is a Vc, divided by U1 minus U2. U1 is the empty pygnometer volume, or U2 is the with sample. This total process is divided by U1 minus US. U1 is the first empty, and US is the state piston denoted by the sample. So first we can calculate it, this calibration parameter by calibration reading, then we get the sample readings. Sample reading is the US. So by this process, incorporating the empty weight, calibration parameter and the sample parameter, we can get the exact true volume of the samples. That is the main process to calibrate the apparatus by using the helium gas and stainless steel spheres.